Let me give you an example of carbon nanotube and gold nanoparticles, like gold nanoparticle decorated carbon nanotubes. Like, one of the things that, can be used for like gas sensing application. Gold nanoparticle is considered very sensitive to like gas like sulfur dioxide and hydrogen sulfide, like the sulfur-based gases, the sour gas, and yeah, it can be used as like decorated on a carbon nanotube to promote the sensitivity of such material, and then the whole thing can be used for like the sensing of sulfur dioxide or hydrogen sulfide. In the process of doing that, on the left hand side is carbon nanotubes, TEM image, of course, and the one on the middle is the carbon nanotube with gold at the certain resolution. This is like 100 nanometer. So the gold nanoparticle would be around like, I would say 10 to 20 nanometer in size. Maybe like, feels like this is, they look closer to the structure. And I would say gold nanoparticle is a little less than 10 nanometer, would be like in like, I don't know, like 5 to 10, yeah, something in that range. And the crystal diffraction, light diffraction pattern telling me that this is like polycrystal. Yeah, and the grain size is kind of big, so it's crystal somehow, but not single crystal. That if you use TM, that's all you know, right? But for the XRD, you can learn a lot more than that in terms of the crystal structure, because like you see the peak, this very first one represent the graphite. That means this one come from carbon nanotubes, and it come from the plane 002 of the carbon nanotubes. The rest, 38.2, 44.4, 64.6, and 27.5. It can be indexed to 111, 200, 220, and 311, plane of the pure base center crystalline gold. So the remarkable thing about the XRD is that the signal of different material or the same material of different crystal structure would appear at different spot on the x-axis. So you wouldn't have much problem of like, it's like two crystal structure has like kind of like signals that kind of like, going combining with one another, created one peak. That happened, but the possibility is lower as compared to other type of analysis. And when you have different type of material, you can kind of see that like it has its own characteristic peak. Like graphite has their own peak, happen at 002, happen at around like 25, and go cover the rest of the peak. And graphite actually offer the peak, but like relatively a lot smaller and broader as compared to gold, which is like peak, sharp and narrow. That the nature of the material. That gold is like metals, so it kind of like has like very close to the single crystal structure. I would say this has a pretty good chance of like has the gold as the single crystal, but since it's being like impaired by the interaction of gold and carbon from the carbon nanotubes, that interaction caused the shift in the peak to occur, or like cause the strain in the structure of the gold nanoparticles, and so it doesn't appear like a single crystal in the light diffraction pattern. But in here, I would have said that like gold actually is like has a pretty good chance of being like a single crystal. It has a pretty good like high peak and sharp, but still it probably shift from the center, or from where it's supposed to be. I don't know about that. It need to look into the database, and if it shift from the position that is supposed to be, let's say like it's supposed to be around like 40, but it actually appear at 38. If I were to analyze it, I would have said like, you know, like gold nanoparticles has a significant amount of strain in the structure, in the crystal structure, and that could be from the interaction of gold and the carbon nanotubes, or you know, the gold nanoparticles probably like being pressed, or like it turned to like started to transform into some other phases, those sort of thing. That's something that we can analyze from the XRD as well. But normally, like you only need to tell the story that you need to tell. So if the transformation in crystal structure doesn't interest you, it's not supposed to be analyzed that way. So at the end of the day, XRD still need to be used as one analytical result along with so many that you know you build them up to tell the story that you would like to tell. You need to at the end of the day, all you need to see is the trend, not like certain peak or like not the specific thing. You need to see the trend. So it's like the temperature that you use for the annealing system, like to anneal the material, cause the different structure in the crystal structure. And it appear on the SEM, on the TEM, and on the XRD, you see different phases happen too. So that's the kind of story that you would like to tell, not like drawing everything out of like single analytical result, right? I'm sure you like understand. The other interesting point that I can draw from this experiment is that gold nanoparticles actually maintain its original structure and original property, right? Even if they are staying together with the carbon nanotube. So that means like I can assume that like not much interaction happened between carbon nanotube and gold nanoparticles. They just like stay together, attached together, but they're not changing one another. One is not disturbed by the presence of the other. It's just attached together with like chemical bond or like physical bond whatsoever. But crystallographically, it maintains its original structure. That's what I'm saying, and it's like that's what I'm trying to draw from the XRD curve here. This is another example of the graphene and gold nano composite. So we have gold nanoparticles that decorated on graphene, and this one on this one you can see like obvious result that like for the graphene oxide, you have the peak down here from the reduced graphene oxide, which is also the graphene oxide, but less amount of like functional groups. The peak still look like that, which is like pretty much the same on the XRD. So by reducing the graphene oxide to reduce graphene oxide, it doesn't really like affect much of the crystal structure. It's just that you remove some functional group from it and make electron flow easier. Well, you know, I'm a nerd. What can I say? So it's like the one at the top is the reduced graphene oxide with gold nanoparticles. So you can see graphene oxide here, and you can see gold peak happening at 111 plane, 200 plane, 220 plane, 311 plane, and 222 plane, which is the same plane that you also observe from the other experiment. It's like it is being done by different group. So 111, 200, 220, and 311, 111, 311. Yes, I was like, but I would say like this guy see more of the peak than the other. He see 222 plane, but it's like the signal is a little like rather small as compared to others. Maybe he got better analytical equipment. I don't know. But anyway, the point is you can see that characteristic peak of the gold nanoparticles are the same in different experiments that being done by different group. That means pretty much these two are having similar crystal structure on that gold nanoparticles. I mean, like roughly speaking, that they have the same crystal structure. But if you want to be very, very precise, what you need to do is like determine the ratio of each and every phases on the sample, or like normalize it somehow. That's like this is the amount of like 111 plane. This is the amount of like 200 plane. The amount of 220 plane, 311 plane, and 222 plane respectively, and compare one with the other. Let's say like, okay, these two didn't provide like the real number here, but anyway, if I were to like make the judgment here and I need to do something here, I would say like, okay, this is like A. I would say this is B, C, and D, and maybe like I just divide everything with A. That means it's like this is the 111 plane, 200 plane, 220 plane, 311 plane, right? And then you can have the height of the peak, the A, B, C, D, respectively. So you can divide it with the same number though, with A, 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 right? You got some kind of number, and that's the ratio that being like normalized using A. You can do the same with the experimental result from the other curve. Let's say this is like A prime, B prime, C prime, D prime, and E prime. I laugh because like that's my style. It's like I don't know how I get it from, but like I teach like all the classes. I use this kind of thing. Like, okay, this is like the constant A, B, C, D, and that's A prime, B prime, you know. A prime, B prime, C prime, and D prime, and E prime, if that matters. So I would divide them all with A prime. It's important that it needs to be normalized using the same peak. And if I can prove that mathematically these two had just about the same number, the ratio that being determined here, it would end up like, you know, closest to one another. I would have said that like these two experiments has the gold nanoparticle with similar crystal structure to one another. Or even like when you do your experiment too, if you try to see like one guy is doing experiment and he got one thing, the other guy doing experiment and he got the other thing. Let's say like you have like your seniors in your lab, and he's working on like say like carbon nanotubes, and he has like XRD curve like being written or like published like a while ago, and then you know got trained by him, and he left, and after that you would like to know how is your sample as compared to his. So you operate XRD and normalize your curve and compare it that way. That way, you'll be able to tell how the similarity between the two samples crystallographically. I'm going too deep here, but I'm pretty sure it's like what I'm saying here is gonna be very helpful for you if you actually take this seriously. The other sample, I have a lot of like metal dope things. So it's like that's what I do. So pardon me. Uh, this one is a silver dope titanium dioxide nanoparticles, and titanium dioxide has three known phases: anatase, rutile, and rutile. And in this experiment, they only found two phases, which are anatase and rutile, and they have silver particles as well, silver structure, and you know they name it and they mark it. So they found some peak on the A line, that's the titanium dioxide. So they found some rutile and anatase. On the B picture, they just dope 3% of silver on the titanium dioxide. and they start seeing the silver peak up there. Other thing I see is that some peak changes on the titanium dioxide as well. Root type gone and more unattached, I believe. And in C experiment is the 7% of the silver dope on titanium dioxide and anneal at 450 of the temperature. At that higher temperature, I would say it would become more unattached. Am I right? Of course I am. Yeah, this would be more unattached going on. And more silver nanoparticles too. Because, like after you dope and if you anneal it, there would be more silver nanoparticles in the system. Silver is one metal with low electronegativity. That means like it easily precipitated. So you will be able to find some method to like just precipitated silver nanoparticles at room temperature using just reducing agent. It's not like some ceramic type of like metal oxide, like tin oxide or titanium dioxide or magnesium oxide that require higher temperature in order for it to like become the metal oxide, or else it just became a gel. Silver is a type of metal that became metal at room conditions. So I'm not sure why do they need to burn it, but like that's successful for them. I'm happy for them. Like one large example on a carbon nanotube with metal oxide. This one is cobalt oxide, and they have like very obvious like trend. I love to have this kind of experiment sometime. The cobalt oxide has like obvious peaks happening 111 220 and so on. And for the carbon nanotube they have like another two characteristic peak for the carbon nanotube. One appear around like 25, the other one appear around like 45, yes. And then when they combined it together they found all the characteristic peak. This actually from the 111, right? This actually from the carbon nanotube. I would say one peak of the carbon nanotube is gone, but never mind. It's being like overwhelmed by the a lot higher signal that coming from the cobalt oxide. Right? That's how I analyze the XRD curve, and I'm pretty sure it's like you can absorb something and adapt to your own work as well. So the last thing I would like to talk about XRD is actually one of the most important thing about XRD. It's known as Scherer equation. When you talk about XRD, you talk about crystal structure. And one of the most interesting about the crystal structure is that it can form some sort of like polycrystal. Say, let's say this is the single crystal that consists of like atoms with the same atomic pattern. It forms the structure in the same pattern for the whole material. That's why it's known as single crystal, right? The entire atom in this crystal are having the same pattern, combining with one another and staying with one another. That's a single crystal. But when we talk about like the material that not very electrically conductive, or the material that like has to be like a bulk material, like a big one, right? Instead of just like nanoparticles and single crystal. Like we talk about bulk material here, we probably need to deal with polycrystal. When you deal with a polycrystal, that means like it would also has the same kind of like atomic formation, but there would be separation between each atomic formation. Say there would be grains, right? It would try actually like it actually like try to grow into like crystal, but it's a big plane, so it's like it has like it start in different position, and when it start in different position, when it start like going like bigger, it cannot just like bind with one another that easily. So it became like polycrystal. for the polycrystal, just like when we talk about, just like when we study the light diffraction pattern, the polycrystal that has the big grain size, that means like each and every crystal is big. So in one material, it wouldn't have so many of the crystal. So the whole thing is pretty close to the single crystal, right? Our crystallinity level is pretty high on a polycrystal with a bigger grain. That's what we tend to learn from the light diffraction pattern, right? For the XRD, we can go do one better. The better one is that we can find the size of this grain. Number, we would get the number of this grain as like the material with the bigger size of the grain would be more crystalline than the other. We can have that kind of idea. So it's like that's where the Schroeder equations come from. But it only be accurate if the grain size that you determine, the number that you obtain in the end is less than 200 nanometer. If the number that you obtain in the end is bigger than 200 nanometer, the Schroeder equation can no longer be applied. Or it could be applied, but at significant level of error, right? So it's only good when the crystal size is or the grain size is less than 200 nanometer. So it would be called like crystalline size. Crystal light size. That's the technical term for it. The crystalline size is the average number of the grain size, and it represents as the alphabet. The crystalline size of the domain, of the crystalline domain, and the K is the dimensionless factor or the shape factor, which is like for the spherical shape, it would be close to 1. Sphere is close to 1. For the cubic would be close to 2. For, I don't know, nanowire, it would be close to 0.68. So where is your sample? Up to you to decide. All right. Spherical, let's say like, okay, to be accurate, spherical has a shape factor of 0.94. Cubic has a shape factor of 2.08. And nanowire has the shape factor of 0.68. Choose it at your own risk and your own decision, right? Depending on like the size of your sample or like the shape of your sample or the shape of the crystalline size. That like take it as you may. And the lambda is the X-ray wavelength, which is in the unit of angstrom. It's equal to 1.41 in case of copper target material in the light bulb, and it equal to 0.71 in case of molybdenum target in the light bulb. As told you like earlier, that's like that, you need to ask the operator. That could be important later on. The grain size supposed to be like less than 0.1 to 0.2 micrometer, which is like 200 nanometer. And beta is the line broadening at half of the maximum intensity, which is the width of the highest peak at, the size. This value is known as FWHM. The line broadening half the maximum intensity, full width at half This one is also known as FWHM, which stand for full width at the half maximum. So it's like if your peak is like sharp and tall, it has the intensity of high. So the height at the I divided by 2, from that position, you monitor the width of that peak. And it would be beta. And theta is the bright angle, which is like the tip of your peak. Gonna be theta data. This is another picture that represents like, you know, how to monitor the beta value, which is the peak with full width at half maximum. So it's like you have a peak here, and this is like the maximum intensity at half the maximum intensity, which is like this height. You monitor the width in the unit, the same unit as theta. That would be the value of the beta. To make sure you understand this better, I would like brought like a data from, you know, my old paper on the composite material of copper oxide and titanium dioxide graphene. We characterize it using the XRD, and there would be like one titanium dioxide reduced graphene oxide sample and titanium dioxide sample, and we have the one that like dope further with the copper oxide on titanium dioxide graphene, and we have like the copper oxide that dope on the P25 reduced graphene oxide, and these are the sample that we obtained. Let's say I chose one peak, and this is the baseline of the peak. So I monitor the height of that peak and divided by 2. At that point, I monitor the width of the peak. Whatever I obtain, I put it as the beta value for the Scherer equation. So let's say I got 3 degrees from the beta value. I change it into the unit of radians. This depends on the unit that you use for the other variable. Let's say like if you change it into the radian, that you gotta make sure that whatever you obtain from the cos theta here is in the unit of radians. So it's like it needs to like, you know, like the unit needs to just like be the same with one another. And the beta is the in the radian unit, and like the cos theta in the union in the radian unit, and then the theta is like the tip of the peak here around 26. So cos radian 26 coming out in the unit of 26 in the unit of radians, and then 3 degree, right, 4 point something radian. This is like the beta value. The K shape I use around like 4.9, which is like because titanium nanoparticles is rather spherical, and the lambda value is around like 1.54, which is like from the copper, that from the manual that like I obtained from the operator. And then the final number would be around like 2.92 nanometer. That the size, the crystallized size of the sample that I use. And I can extract this value from the XRD. Once again, this would be very helpful to you if you take this seriously and I don't know, like engage in the calculation here. And I I I would have you do this for the midterm exam as well. So it's like be ready. Okay. That would be it for today. I sure hope that you guys stay healthy, and I'll be seeing you guys next week.